question is now, of course, what's with validation of this, right? And validation starts with inter and intra-observer variation investigations, and there you will find these two publications, one from Germany in Heidelberg and the other one from the Netherlands, showing that this concept, and if I talk now about concept, I mean this A4 clinic software, has a very low variability with respect to inter and inter-observer variation. The latest data, though, comes from the James Cook University in Australia, showing that we have a 3.3% intra-operator coefficient of variation for peak wall stress, and this also relates to peak wall rupture index, and a 1.6% variation for maximum diameter. And I think this is unmatched, so you will not find any clinically applied software which can provide such accurate diameter measurements like this. Right, so now we have a nice software with low inter and inter-observer variation, but it still does not tell you if that helps you in rupture risk assessment. So now the next one is that you will find several studies out there which pose basically the question, do biomechanical indices discriminate between ruptured and non-ruptured aneurysms? And also with comparison to diameters. Do they discriminate better than diameters? Going back to 2002, Billinger and all posted this question and investigated this, up to our own studies here, and all of these studies come to the same conclusion that peak wall stress and or peak wall rupture index is superior to diameter. Now recently we did also a very similar study together with Karolinska Institute in Stockholm, Liège University in Belgium, and the Heidelberg University in Germany, where we investigated 203 non-ruptured cases and compared them to 40 ruptured cases. Of course, the ruptured cases were much larger than the non-ruptured cases, and it's not surprisingly that peak wall stress and peak wall rupture index are much larger in the ruptured group here compared to the non-ruptured group, right? Because also the diameter was larger. So we had to do a more sophisticated comparison, and this sophisticated comparison is shown here. So what we did is we compared these biomechanical equivalent diameters, what we introduced before, so this rupture risk equivalent diameters, with the geometric, with the geometry diameter. And what this is the difference between the rupture risk equivalent diameter and the geometrical diameter. And for the non-ruptured cases, this difference has to be 0 because that was the definition of this diameter. However, if we look to the ruptured cases, we see even already for peak wall stress a statistically significant increase by about 7 mm. That tells you that in the ruptured cases, the risk equivalent diameter was 7 mm larger than the geometrical diameter. That explains why this group ruptured and this one not. If we look then to the peak wall risk index, then the picture gets even much clearer. So what we see here is that again, the non-ruptured group, the difference between biomechanical equivalent diameter and geometrical diameter is 0 because that was the definition. However, in the ruptured group, we have an increase of 17 millimeters. And this tells you that in the ruptured group, the rupture risk equivalent diameter was 17 millimeters larger than the geometrical diameter, and explains why this group ruptures. Still, you observe also a large overlap between the non-ruptured group and the ruptured group, and that is simply because this rupture is to some extent a stochastic event. Even an aneurysm at low risk of rupture will rupture if you just increase the blood pressure high enough. Right, then we have also other types of validation. So there's this study in 2011 where males were compared to females with the conclusion that females at the same size of aneurysms are at higher risk of rupture, which is also seen, of course, clinically. And then there is also histological validation, where this group in Heidelberg compared or investigated histological changes in the aneurysm wall and correlated that to stress, and came to the conclusion that higher stress or higher risk of rupture leads to signs of inflammation, calcification, and so on. So this is another issue. Finally, there is also this plot I'd like to introduce. What we did there is we compared peak wall rupture index with estimated annual rupture risk provided by several studies in the literature. And what you see is this is one of the lowest curves you will find in the literature, which tells you how annual rupture risk increases with diameter, and this is one of the larger ones. And now our risk index is somewhere in between here and has a very similar shape than these experimental curves. And what this curve also tells you is that the risk index of, let's say, 0.56 correlates to an annual risk of rupture of about 15%. So now we have another very nice interpretation of our index in terms of estimated annual rupture.